Alright, continuing with this series of videos examining the lectures of Professor Walter Lewin of MIT and such. This is a review video, so it's for a test. Yeah. So we're getting down to the last couple of videos, so strange final test told me it was on 3 lectures, I guess, but it doesn't matter. Continuing.
Can I cover all of them, of course, during the exam? I can only touch upon a few of them. And what I cannot cover today, what I will not cover today, can and will be on the exam.
Tells them the same thing every time.
Let's first look at magnetic materials.
Cool.
Magnetic materials come in dia, para, and ferromagnetic materials. The molecules and the atoms in para and ferromagnetic materials have intrinsic magnetic dipole moments. These have always...
Alright, so right there I think he's in trouble because they obviously line up very differently. So ferromagnetic, what you essentially do when you expose it to a magnetic field is the dipoles line up just like the other magnet and they reinforce each other. In the sense that they line up opposite. So they feel the magnetic field, they react to the magnetic field. The dipole ones, the paramagnetic ones, do exactly the opposite, in the sense that they misalign to the magnetic field. The magnetic field is inducing in them some other kind of effect, affecting the atoms and turning them into essentially monopole charges. And that's what you get back. And it's the same charge. So what the magnet is ends up being what the paramagnetic material produces, so it becomes an opposing force. Really huge distinction.
It's always a multiple of the Bohr magneton. Has to do with quantum mechanics. It's not part of 802.
Nope.
And they are going to be aligned by the external field. I call that the vacuum field.
So why they call it a vacuum field when it's a magnet or an inductor or some real thing? It's not a vacuum thing.
And the degree of success depends on the temperature and on the strength of that external field.
So again, the two have to be distinctly recognized as having completely different opposite reactions to exposure to the field. The ferromagnetic will create attraction and the paramagnetic will create repulsion.
The lower the temperature, the easier it is to align them, to overcome the thermal agitation. And above a certain temperature, which we call the Curie temperature, ferromagnetic material loses all its qualities and becomes paramagnetic. And I have demonstrated that during my lectures.
You haven't demonstrated that it becomes paramagnetic, that now it reacts to a magnetic field by creating the same exact field in response and being repulsive. So that wasn't demonstrated.
Suppose we have a solenoid, and the solenoid has n windings, and the length of the solenoid is n, and the current I is flowing through the solenoid. Then the magnetic field generated by that solenoid, which I've called the vacuum field.
Again, a vacuum field. But anyway, what they never show in the experiment either is putting a paramagnetic material in the solenoid. So put a copper rod in there and see what happens. This isn't going to be the same thing as the ferromagnetic. Completely different reaction.
That magnetic field can be derived using Ampere's law, which you see down there. That magnetic field is approximately mu0 times I times n divided by L. If now I put in here ferromagnetic material, then...
So the only part that really matters is it's the length and the number of windings is going to dictate to you how big a collection of field you're going to get, how much of the field you're going to collect. And obviously the amount of current going through the wire, which is deciding how magnetic the coil is.
I have to include this factor kappa of m, or k of m, whatever you want to call it, the magnetic permeability. And this can be huge. This can be 10, 100, even up to 1,000 and higher. So you get an enormous increase.
So that's the kappa m is if you add the ferromagnetic material. I don't think he made that clear, but that's if you add the ferromagnetic material.
Magnetic field strength. Self-inductance is defined as magnetic flux divided by the current I. That's just the definition of self-inductance. If the magnetic field goes up by a factor of kappa m, then of course the magnetic flux will go up by the same factor, and so the self-inductance will go up. You may remember a demonstration that I did when I had an iron core which I moved inside the solenoid, and depending upon how far I moved it in, could we see that the self-inductance went up, and when I pulled it out, self-inductance went down again.
Essentially the amount of resistance, the slowness of the ability of the inductor to react. Because the magnetic field gets stronger and stronger, everything gets more lag because it's harder to drag things around, essentially. So you start killing frequencies, high frequencies, the more load you have in the magnet.
We have an interesting problem. I think it is assignment 7, whereby we have iron core here, and then we have somewhere an air gap, and you may want to revisit that to refresh your memory. So let's now turn to transformers. The transformer often comes in this shape. Let me move it a little bit to the right. Often comes in this shape, which is then ferromagnetic material. To give perfect coupling between the left and the right sides, also increases the magnetic field. This is the, let's call this the primary side. N1 windings, index, self-inductance L1. And here I put in a voltmeter to always monitor that value. I call that V1. And this is the secondary side. N2 windings, self-inductance L2. And I put here a voltmeter which always monitors that voltage. And I call that one V2. You can show with Faraday's law, as I did in class, in lectures, that V2 divided by V1, let's not worry about plus or minus signs, is N2 divided by N1. That's a good approximation.
So 1-to-1 relationship, or 2-to-1 relationship, how we look at it, between the coil number and the voltage number. So you want to increase the voltage. If you want to double it, you just 2 coils. Simple.
Depends on how well the coupling goes. It depends on several factors, but you can come very close to this. And this means then that if you make N2 larger than N1, then you can step up in voltage. We call it a step-up transformer. But you can also step down if you make N2 smaller than N1. Under very special conditions, will the power generated on the primary side be all consumed for 100% or nearly 100% on the secondary side? That is very, very special. If that's the case, then the time averaged power here, V1 I1, is the same as V2 I2 here, time averaged. And so as a logical consequence of that, you'll find that I2 divided by I1, let's not worry about minus signs, is that N1 divided by N2. That, however, is not so easy as you may think.
Always heat and different things happen, so you lose losses in most systems. No perfect system.
Only can work approximately, and I mentioned that on the side in my lectures, if the resistance here and the resistance there is way, way smaller than the value for omega L. And we did try to achieve that during one of the demonstrations that I gave on this. I remember we had the induction oven, whereby N2 was 1, and N1 was very large. I don't remember what it was anymore, but it was of the order of several hundred, maybe 1,000. And we managed to get a current in the secondary, which was huge, which was close to 1,000 amperes. It was enough to melt that iron nail. And we made every effort then to make sure that the resistance was much, much smaller than omega L. I think problem 7.1 of our assignment deals with that, and very naively assumes that this is all true. But you should realize that it is not always so easy to achieve the conditions for that. So let's now go to RLC circuits there. Let's take a system which has a resistor R, it has a self-inductor, a pure self-inductor L, and a capacitance C, AC, and this driving power supply provides with a voltage V, which is V0 times cosine omega t. Keep in mind that this can always be sine omega t, of course. There's nothing special about a cosine in life. The steady state solution, that is not when you turn the thing on, but if you wait a while, you get a steady state solution for the current. And the current that is going to flow now is V0 divided by the square root of R squared plus omega L minus 1 over omega C squared times the cosine of omega t minus phi. And the tangent of phi is omega L minus 1 over omega C divided by R. We call this the reactance upstairs, for which we give often the symbol X, and so this is also X, then divided by R. And this whole square root that we have here, we call that the impedance. The units are ohms, and we call that Z. And so the maximum current that you can have, the current is of course oscillating with angular frequency omega, the maximum value that you can have for the current, which I call I max, is then V0 divided by Z. And the cosine term is either plus or minus 1.
Not much needs to be said there. The frequency gets trapped between the inductor and the capacitor, and it has its own resonance.
Can plot now this I max as a function of frequency. So here is frequency, and here is I max. If the frequency is very low or near 0, then this term here becomes infinitely high, this impedance is infinitely high, and so the current is 0. I max is 0, there's no current flowing at all. When we go to very high frequencies, it is the omega L term that goes to infinity. And so again Z goes to infinity, so again I max goes to 0. And for other values of omega, you get an I max which is not 0, and so you get a curve like this, which has the name of resonance curve. This I max reaches a maximum value when the system is at resonance, that's what we call resonance, and that's the case clearly when the reactance is 0. Because when the reactance is 0, this part vanishes. And if the reactance is not 0, then...
So it's just basically trying to tune the circuit so the oscillation going between the capacitor and the inductor is the same frequency as the frequency of the current you're putting in to the system.
The maximum current can only be lower, can never be higher. And so when x equals 0, you'll find that omega L is 1 divided by omega C. And so the frequency for which that happens, I call that omega 0, reminds me that it is the resonance is 1 divided by the square root of LC. When I am at resonance, phi becomes 0. So there is no phase delay between current and the driving voltage. They are in phase with each other.
Well, they have to be. That's the whole point. So if they're not in phase with each other, then they're destroying each other. So.
And the value for I max now simply becomes V0 divided by R, because the impedance itself becomes R. Very boring, very simple. You're looking here at Ohm's law. When the system is at resonance, forget the self-inductance, forget the capacitor. They are not there. They annihilate each other. So the system behaves as if they were only a resistor. And that's exactly what you see here.
Yeah, it's the opposite, really. They don't annihilate each other. They do exactly the opposite. They're compatible with the movement. So when the current's going this way, the inductance is also compatible with going that way because it's feeding the capacitor. And when it's going the opposite way, the capacitor is already feeding the inductor, so it just goes in the same flow.
I have here some numbers which you have seen before during my lectures. You can download this from the web, but you have to go back to the lecture when I discuss that. And you see here some numbers for R, L, and C, and also for V0. And I calculate for you here the resonance frequency. I calculate the frequency also in terms of kilohertz. And here you see the impedance, and here you see the reactance. If I'm 10% below resonance, notice that the 1 over omega C term is always larger than omega L. So your reactance in this case becomes minus 86 ohms. The minus sign has of course no consequence for the current because you have an x squared here. But notice that Z is now almost exclusively determined by x and not by R anymore. Because the 10 ohms of the R here play no role, almost no role, in comparison with the 86. Z becomes 87, and the maximum current is 1/10 of an ampere. When you're on resonance, and that is characteristic for on resonance, the 2 omega L and 1 over omega C eat each other up, they annihilate each other, and so the reactance becomes 0. So Z now is just pure R, x is 0, and so the maximum current in this case is 1, because I chose V0 at 10, and I chose R10.
So again, I would just, a small quibble, but I just wouldn't describe it as as the reactance, because the reactance is a negative thing. So that's what you're eliminating, is the fact that they're out of phase. So you're stopping the capacitor and the inductor from trying to do the same thing at the same time, which is the negative thing, and so now they're compliant to the flow of the current. Not just say it different.
And then when I'm 10% above resonance, then the omega L term is larger than the reactance of the capacitor, and accordingly you get a lower current again, about 1/8 of an ampere. And so you see this curve being formed in a very natural way, and that's quantitative. You see there some numbers. So now comes the question, which of course in practice is very important, and that has to do with the power that is generated by the power supply. That power comes out in the form of heat in the resistor, and so if you time average the power, then the time average value, you can take the voltage, the power supply, multiply that by the current. You could also take the time average value of I squared R, because all that energy will ultimately come out in the form of heat of the resistor. Either one will be fine. I've decided to take this one. So I will get then V0 cosine omega t. The I becomes V0 divided by Z times the cosine omega t minus phi. This is the power at any moment in time. I will do the time averaging a little later. When I see cosine omega t minus phi, that reminds me of my high school days. Cosine alpha minus cosine alpha minus beta is cosine alpha cosine beta plus sine alpha sine beta. That was drilled into my memory here. I will never forget that, I think. And so I will write down here, my math teacher will be proud of me, cosine omega t cosine phi plus sine omega t sine phi. So this is this term. If I'm going to time average it, I have a cosine
Doesn't seem like a simplification to me, but whatever.
omega t multiplied by sine omega t. That time average is 0. So this term vanishes. So the time average value of the power, I get a V0 squared. I get a Z here. And now I have here cosine omega t times cosine omega t. The time average value of cosine squared omega t is 1/2. So I get a 2 here. And then I still have my cosine phi there. And I'm done. If you like to get rid of this cosine phi, you can do that. Because remember, the way that phi is defined, the tangent of phi is the reactance divided by R. You still see it there. So that means if this angle is 90 degrees, that this side must be Z. That's the square root of x squared plus R squared. That's this part. And so the cosine of phi is also R divided by Z. And so if you prefer that, there's no particular advantage, but if you prefer that, you can write down for cosine phi R divided by Z. And so you get V0 squared times R divided by 2. And now you get Z squared. And so there you see the power, time average power, in an RLC circuit. So now we can look at resonance. It's always a very special situation. When we are at resonance, Z equals R. So you replace this capital Z by R, and then you find V0 squared divided by 2R. That's utterly trivial. You could have predicted that. It's really Ohm's law staring you in the face. There is no self-inductance, there is no capacitor at resonance, so you might as well have treated it as a simple system only with R.
So at very low current, you keep a lot of it, and so it starts to degrade the higher you go, because the current is squared, and you're dividing it by 2. So yes, at low current, those numbers will be closer, and at the square will take care of the 2's, will cross out, so to speak. And the further you go, the more the difference between the square and dividing by 2.
And you find immediately then that answer. At any other frequency than omega 0, Z would always be larger than R. You see that immediately here. And so that means that the average power would always be lower. So it's only at resonance that you generate the highest power possible. All right, let's go back to our subjects and see what's next. We did LRC circuits. Oh yes, we're getting now to traveling waves and standing waves. Let's start with a traveling wave in a string. It's always very nice to do that because the parallel with electromagnetic waves is nearly 100%. I have a string that oscillates in the y direction, and let's say it propagates in the x direction, y0, cosine, kx minus omega t. When I see this traveling wave, so the traveling wave in the y direction, and it propagates in the x direction, I see immediately that it goes into the plus x direction. So it has a minus sign here, it tells me in the plus x direction. K gives me all the information on the wavelengths, it's 2 pi divided by lambda. Omega equals 2 pi times f, f being the frequency in hertz, would also be 2 pi divided by capital T now being the period of one complete oscillation. The speed of propagation, the disturbance propagates in the x direction, is omega divided by k. And so,
so this is another one of those cases where they have these 3 terms to define frequency, and so you could have wrote it a third way, because there's frequency in hertz, and then there's period, which he called time, t, which is in a sense the wavelength, right? Well, period would be the same as frequency. They wouldn't. He's claiming the period would be measured as an opposite number. So the period goes down as the frequency goes up. So it's the same as the period would be the same as the wavelength. So he could have just said the wavelength. It's just really annoying.
I draw here, at a particular moment in time, this string, and this would be y0, that would also be y0, and it would propagate in this direction with that velocity, and this would be the wavelength, lambda, and that lambda is v times t. It's immediately obvious. If something propagates with the speed v, and it has t seconds to go for one oscillation, it moves over a distance lambda. That's 801. Do not confuse this speed of propagation with which the disturbance moves with the actual speed of the atoms, of the particles in the string. If you were a particle in the string, and you were sitting here, you never move in this direction. Your motion is only in the y direction. You go from here to there, and you oscillate back and forth with that frequency, angular frequency omega. And so if you're really interested in the speed with which you are moving up and down, that, of course, that speed, which we call the transverse speed, is dy dt. And you have to do that then for a particular location, x, which you can choose, wherever you want to sit on that string. And I think we had a problem once where we asked you, the homework, what the transverse speed was. So if now move to electromagnetic waves, then...
So I think the argument would be is if you did think of it just as how fast you're moving up and down, you would move up and down faster than certainly the wave is moving. If you thought about it as speed over the distance, like if you stayed on this point, you presumed you moved the whole length of the wave, that would have to be a faster speed because it's more distance. Yeah, have to be.
Very little changes. Take an electromagnetic wave, a plane wave, where the E vector is in the y direction. So E, E0, there's a unit vector in the y direction, cosine kx minus omega t. This could be a sine, of course. There's nothing special in life with the cosine. I come to the same conclusion. The wave is traveling in the plus x direction, and the velocity, speed of propagation, is omega divided by k. And if this is vacuum, which will I assume for now, then that is c. And as we have seen from Maxwell's equations, c is 1 divided by the square root of epsilon 0 mu 0. Surprising as that is, that comes out of Maxwell's equation.
Right. So they say surprising as that is, as if they predicted the speed of light, when no, they did exactly what the equations required. The E0 and the mu 0, the epsilon 0 and the mu 0 are made up constants. So it's not a surprise that the two constants they're using for the electric field and the magnetic field would add up to c, which is the speed of the actual force. So the force is, this is essentially saying, in a way, there's not two forces. There's one force, and it's traveling c.
And so, if now you were asked, which would be a natural thing for me to ask you, what is the associated magnetic field? Well, the magnetic field is perpendicular.
So again, all they do is put the value of the field in either the E or the B. So they say, look, this one doesn't have any E field, or it has no B field. And what they really do is just putting all the weight in one of them, but they're keeping the constants. So the speed will stay c because they're considering a zero B field is still a field that has meaning.
Perpendicular to the direction of propagation. It's also perpendicular to E. And B0 is E0 divided by c in vacuum. And so, if I make a coordinate system, this is x, this is y, and this is z. Notice that my coordinate system always is chosen so that x roof cross y roof is z roof. This is called a right-handed coordinate system. If you choose any other system, you're an idiot. You always get yourself into trouble. Make sure that you always choose this as a coordinate system. And notice I have x cross y is z coming out of the blackboard. At a particular moment in time, let's say the E vector is in this direction, in the y direction. I pick a random moment in time and I pick a random location for x. Now I must be sure that E cross B is in the direction of propagation. So E cross B must be, in this case, in the direction of x, because it's going in the plus x direction.
They're just saying they're multiplying vectors, so they're just saying the pointing thing. So that's the little hat thing is a pointing thing. The pointing thing has both a velocity and a direction, so it has two components, so that's why they roof it. But it's just adding vectors.
And so my problem is solved. I know that that can only happen if B is in this direction. At this moment in time, at this location. And that's all I need. Because now I can write down that the B vector that is associated with that electric field is E0 divided by C. That is the largest value that the magnetic field can have, times the same cosine kx minus omega t. And now I must have here z roof, and now I'm in business. So now I have the E vector that goes with the B vector that goes with the E vector. We would often be
And then you combine those two, and you'll actually find out where their field's really going, actually. I mean, those the actual field will be moving in the combination of those two.
Interested in energy, how much energy per unit area per unit time is in the plane wave. That is given by the pointing vector S, which is E cross B divided by mu 0. We're still in vacuum. We still assume that it's all vacuum, so this is watts per square meter. Of course, we are in general not interested in the instantaneous value of the pointing vector. Who cares about that? It oscillates like mad. I'm more interested in the time average value. And so the time average value, this has a cosine omega t, this has a cosine omega t. The product averages out to be 1/2 of cosine square omega t. I get an E0, I get a B0, and I get a mu 0. And if now you want to get rid of your B0, because you want to get everything in terms of E0, you can replace B0 by E0 divided by C. And so this would also be fine. E0 squared divided by mu 0 C. And so now we have the time average value of the pointing vector. The moment that you move to
The 1/2 probably deals with the mu 0 being 1/2 of the speed of light, kind of a thing, blah, blah, blah.
vacuum, from vacuum to matter. So we now go from vacuum, we move to matter, and the matter has dielectric constant K, and it has magnetic permeability K of M. That's only important if we deal with ferromagnetism, because with paramagnetism and diamagnetism, K of M is always, practically for all practical purposes, 1. The kappa can vary a great deal from the various substances. And so now, all you have to do, if you go to Maxwell's equations, if they were given only in vacuum, then you have to replace epsilon 0 by kappa epsilon 0. That's already done there. And you have to replace mu 0 by kappa m times mu 0. And therefore you have to place C by V, because the velocity is different in matter of electromagnetic radiation. And you see immediately how it changes, because epsilon 0 and mu 0 have to be replaced by epsilon 0 k and mu 0 kappa of m. And so you see here that the velocity following my recipe becomes epsilon 0 mu 0 kappa kappa m. And so my B0 becomes now E0 divided by V and no longer divided by C. So this B0 becomes E0 divided by V. Kappa can be a very strong function of frequency, so can kappa m, but kappa m of course is only important for ferromagnetic materials. I've shown you an example before that kappa, the dielectric constant for water, was 80 at low frequencies, even at 100 megahertz radio frequencies. It was still 80, but at the visible light, where you're dealing with frequencies of a few times 10 to the 14 hertz, that value for kappa was way lower, was 1.77. And so kappa is a small function, a strong function of frequency, and we introduced index of refraction, which is C divided by V. And since V itself is a strong function of frequency, the index of refraction can also be a very strong function of frequency. It was 1.3 roughly for water, but it's a little different for red light, from blue light. If not, we wouldn't be able to see rainbows.
That's probably enough. So, till the next time. I didn't like these mixing the light subjects with the electricity subject with the, E field, B field subject. But that's what they do. That's their thing. So anyway, till the next time, such.